This is our first video on transformers. You meet transformers everywhere in everyday life, but you just don't think about them. So here's a couple of examples. This particular unit is from my printer. I can't remember what the output voltage is, but the input is 230 volts AC, and the output from this, I think it was something unusual like 16 volts, which is very unusual. And this sort of thing you'll all be very used to, a phone charger, so 230 volts in, and out of the top we get 5 volts to charge our phones. And they don't just appear like that. You will have transformers in many household appliances, whether that be a microwave, an oven, a television, a DVD, video recorder, whatever, hi-fi amplifier. They all need to be supplied, so the electronics needs to be supplied at a low voltage, and electronics tends not to work directly off AC. It's not always true, but 99% of the time it is. So we have to transform the voltage down and then fiddle with it, which we'll cover when we hit electronics itself. So transformers, let's have a quick look. They appear in two types. So we can have step up, in a step up transformer we may have, for example, 230 volts AC on the input, and on the output we would have a higher voltage. It could be 400 volts, 1000 volts, 10,000 volts, whatever it is. Let me stick with 400 volts. So our input is 230 volts, the output is higher, step up. Step down is the next one. Step down transformer. This is most of the transformers that you're going to encounter, and in domestic work. 230 volts in. For your TV, there could be a range of different voltages, 5 volts, 12 volts, 24 volts. For the phone charger, which I showed just a moment ago, that's 230 volts in, 5 volts out. So whichever way it goes, whatever voltage we end up with, we want a low voltage out. So that's step down. Let's move on to the next little bit. And let's identify the parts of the transformer. We have two distinct windings. The first winding is called the primary. So primary or first. Primary. And the output side is called the secondary. So primary winding, secondary winding. Transformers work on AC, so this will be AC, and this is our input voltage, which we'll connect here. This all works on AC, and the idea of the transformer is to transfer the voltage from one level to another, and it's done through magnetism. We'll explain that in a moment. But on the output side, on the secondary, we're going to take our output voltage, which is again AC, and that's going to appear at these terminals, and this is usually smaller than that. So primary, secondary, input voltage, output voltage. And the bit that I've missed here is we don't just have two random coils of wire, they are usually wound onto iron, and these two lines represent the iron core. So the iron core is the central structure around which our windings, or the wires, the coils, are placed. Okay, so swiftly on then. The next part of your handout asks, what is the meaning of the word mutual? Well, mutual has a couple of different meanings, but in the sense that we want it, it tends to mean shared or together. So something that is sharing something or something that's working together. Let's move on to my next page. So I want to continue with that term mutual because I want to explain is how a transformer works, and it uses something called mutual inductance. Let me try to explain. On this diagram of a transformer, I haven't put in the iron core deliberately just to remove the clutter from the diagram. This is a galvanometer. If current flows down here, the needle moves to the right. If current flows up there, the needle moves to the left. So this is a center reading ammeter. I've got a battery and a switch. I'm going to stress this, transformers do not work on DC. I'm just using this to explain the principle. Okay, there's a battery that provides our EMF, our voltage. Here I have a switch. If we close that switch, then a current begins to flow. So if we close that switch, current begins to flow. If current flows into a coil, it produces an electromagnet. So what will happen now is the flux is radiating outwards from this. As the current grows in size, the flux expands outwards. And here we can see, as the flux is moving outwards, the lines of flux cut through the turns, that is the winding on the secondary of the transformer. So the flux cuts through the turns on the secondary, and if we have the basics for generation, coil magnet movement, this results in an EMF being generated in the secondary. So what we'll have, we'll generate a voltage here, and that will result in a current traveling around here. So for an instant, just an instant, the needle will move over. And I say it's only going to last an instant because this is DC. Once the current has stabilized, it's a set, fixed voltage. The current will stay at a fixed level, and this is a stationary magnetic field. It's not moving. So if it's not moving, that needle will return back to zero. And it will stay there for as long as we want. The only thing that's going to change it is when we open that switch again. So we break the circuit, we stop this current flowing. When we stop the current flowing, this magnetic field collapses. It collapses back into this winding. And if it's collapsing, then now these lines of flux are moving back the other way over this. So the lines of flux are now moving back, and we will induce an EMF in this, which will produce a current in the opposite direction. So momentarily, we'll produce an EMF which will result in a current going in the other direction. This is mutual inductance, where we have a transfer of EMF from the primary to the secondary caused by magnetism. You may want to revisit that diagram several times. This is a common exam question. Okay, so moving on from that, let's have a brief talk about the construction of transformers. Transformers tend to appear in three different constructions. The first one is called a core. That's quite handy because all three of these could be called a core or a former. So very swiftly, what we'll do is we'll wind the primary winding around this and the secondary around that. So primary and secondary, the idea is this iron shape will carry the magnetic flux effectively from the primary to the secondary to make the best use of the transformer. So the next type is a shell. For most transformers that you will work on, this is the appearance of the majority of them. What happens here is, and this is explained in detail in the handout pages that follow, the windings go on the central limb. And to keep it simple, the primary is wrapped around the central limb there, and the secondary is there. So primary, secondary, all in the middle, and this makes very effective use of the magnetic field. The final one is a specialist transformer. This is called a toroid, or it is a toroidal transformer. A toroid is a ring, something like an inner tube for a car tyre, apologies, or something like that, or a rubber ring you might go swimming with. So that would be a toroid. And once again, we would wrap the primary onto there, and the secondary would be on there. Okay, so a toroid has very specific uses, quite specialist. The main one that you're going to encounter will possibly be in hi-fi amplifiers, high quality audio amplifier equipment. So let's talk a little more about the construction of these. Now let's look at separation. Electrical separation is very important to you guys as electricians because it's a safety feature. If we look at how a transformer is made, then the primary, and here is windings, never touch the secondary. So the primary windings and the secondary windings do not touch. That is a safety feature for you, and what that means is if you have a 230 volt primary and, for the sake of arguments, 110 volt secondary, then it is not possible for the 230 volts on the primary to touch any of the secondary windings. So if something goes wrong, you will not get a 230 volt shock. So I'm sure that many of you carry out on site a yellow box which has a 110 transformer in. And what is happening there is, it's an arrangement like this. There will be an iron core, but here, I wish I hadn't put the S there now, but right here, in some of these transformers, this is center tapped to earth. And that is, again, a safety feature for people working on site. If you were unlucky enough to touch this, you won't get a 110 volt shock, because from earth to there is only 55 volts, and from earth to there is 55 volts. So in short, those two add up to 110, which is what we get out. But if you're unlucky enough to come into contact with this live line, then basically you'll only get a 55 volt shock. Therefore, you have a much reduced chance of it killing you. I've never heard of 55 volts killing anyone. Okay, so we're on the last leg. Losses. transformers are not perfect devices, and there are 4 key types of losses. The first one is called eddy currents. These are unwanted electrical currents that flow in the core of the transformer, and it's caused by electromagnetic induction. As the magnetic flux from the primary goes out and in and out and in and out and in, it passes over the core and it will induce an EMF in the core and make currents flow around it. To try and reduce those currents, we use laminations. So we use a laminated core. You can also watch the video clip right now, there's a link to it on your handout, and it will show you a simple eddy current demonstration. So the second one is copper losses. It doesn't mean anything clever. We're going to use insulated copper wire conductor to make the windings out of. Copper has resistance, and we're then going to pass a current through it, whether it's primary or secondary, and basically from P equals I squared R, the answer to that's in watts, we will generate heat in the cables, the very windings of the transformer. So that's copper losses. The third one is hysteresis. There is a totally separate handout explaining hysteresis in your notes, but hysteresis is the process of magnetizing and demagnetizing a piece of material, and that will have to happen to this transformer core every time we connect an AC supply to it. And if we are magnetizing and demagnetizing something using an electromagnet, then we're wasting energy having to demagnetize it before we can remagnetize it. That's what hysteresis is all about. Refer to the handout. The final one is stray losses. Stray losses. And a little bit more complicated and very unusual if you guys encounter it. But imagine if I had a circuit board, a printed circuit board, and I'm looking down in plan, but over here I have a transformer. So there's a transformer, and I have other components which are made of metal, which are mounted near to it. Then this transformer is radiating magnetic fields in and out at 50 Hertz, just as I described back up here. And what happens is components which are near to the transformer may well be affected by the magnetic flux, and they may well have an EMF induced into them, which makes a tiny current flow in them that we don't want. And we're paying for that one way or the other, so it is a loss. So that is stray losses. So losses, eddy currents, copper losses, hysteresis losses, and stray losses. Every one of these we don't want, but we have to put up with them. So it's about how do we minimize them. Okay, so on to the next handout, where I think we're going to meet some calculations.